All right, let's dive into something that feels like it's straight out of science fiction. We're talking about a groundbreaking new idea in AI that tackles one of its biggest problems. How do you get the raw power of a giant supercomputer-sized model into a device you can actually hold in your hand? I mean, this is the big question, isn't it? We keep hearing about these absolutely mind-blowing AI models, but what if we could shrink that power down, make it accessible, make it practical, and put it right in the palm of your hand? That's the incredible promise we're going to unpack today. Because here's the reality check. The most advanced AIs, these large language models, or LLMs, well, they're absolute giants. They're so massive, and they just eat up so many resources that actually running them is a huge challenge, and that's creating a major bottleneck for innovation. So to really get why the new stuff is so cool, we first have to wrap our heads around the scale of what we're going to call the giant AI problem. This is one of those cases where bigger, it turns out, is definitely not always better. Okay, just to put a number on it, a single large model, the kind with like 175 billion parameters that researchers use, can need at least 350 gigabytes of specialized GPU memory. And look, that's not storage space on a hard drive. That's the active memory it needs just to think. It's wildly expensive and just completely out of reach for most real-world applications. And that just kicks off a whole chain of problems, right? You need enormous amounts of computing power, which means crazy high costs to deploy and operate them. And you can just forget about running these things directly on your phone or your laptop. This whole size dilemma is what's been holding back the next real wave of AI. But what if you didn't have to run the giant model? What if instead you could just teach a smaller one to be just as smart? For years, this is exactly what researchers have been trying to do, using a really clever method that's built on a classic idea, the teacher-student relationship. This process is called knowledge distillation, and the idea behind it is actually super simple but really powerful. You take a huge, all-knowing teacher model, and you have it train a much smaller, way more efficient student model. The whole goal is to pass on the teacher's wisdom without also passing on its massive size. But here's where the real magic happens. It's all about how the teaching is done. You could just give the student the answer key. That's what's called hard targets. But the real breakthrough was when they started using soft targets. This is where the teacher shares its entire thought process, all its probabilities, all its uncertainties. This stuff is sometimes called dark knowledge. Knowing the teacher was, say, 90% sure it's a cat, but also saw a little hint of a fox in there, that helps the student learn the nuance of how to think, not just how to memorize the right answers. So, sounds perfect, right? Well, not quite. There is a pretty big catch. For this whole teacher-student thing to really work, the teacher has to provide a gigantic library of examples. Traditional distillation needs enormous amounts of data, which, you guessed it, can be just as expensive and slow as running the giant model in the first place. And that brings us to a data problem. But this is where our story takes a really fascinating turn, leading to what you could call the rationale revolution, a brand new approach that gives this whole teacher-student idea a brilliant, brilliant upgrade. This new method, it's called distilling step by step, and it's built on one simple yet totally profound idea. Don't just teach the answer, teach the reasoning behind it. So in the world of AI, this step-by-step explanation is called a rationale. Think of it like the AI showing its work in a math problem. It's the logical chain of thought, the why and the how behind an answer, all laid out in plain language. It's not just the final conclusion, it's the justification for it. And honestly, the difference is night and day. Look at the left. With standard distillation, the teacher just spits out the answer 8. But on the right, with this new method, DSS, the teacher provides the full rationale. Sarah starts with 5. She adds 3. 5 plus 3 equals 8. This isn't just a little more information, it's a much higher quality of information. It provides a logical structure, a path the student model can actually follow and learn from. And that is a way more powerful way to learn than just getting a score. The process itself is just elegantly simple. First, you ask the big teacher model for not just an answer, but its reasoning, its rationale. Then, you take that whole package, the reasoning and the final answer, and you use it to train the small student model. So the student doesn't just learn to copy the answer, it learns to actually replicate the logic. Okay, so the theory sounds amazing, but does it actually work in the real world? Let's take a look at the results from the experiments.
Because, spoiler alert, the numbers are pretty stunning.
Across a whole bunch of different tests, the story is incredibly consistent. You can see it clear as day. Standard methods, they'll get you to a certain point. Old school distillation is a little bit better. But distilling step by step consistently blows them both out of the water, hitting a way higher level of performance, all while using less data. And this is where things get truly mind-bending. This isn't just about a student catching up to its teacher. In a lot of cases, the tiny student model, after being trained with these rationales, actually ends up outperforming the giant teacher model it learned from. Okay, get ready for this. On one specific task, a student model with 220 million parameters was able to outperform its teacher, a 540 billion parameter model. Let that sink in. The student was over 2,000 times smaller than the model it beat. So how on earth did it pull that off? It's all about efficiency. On average, this new DSS method needed over 50% less training data than the other methods to get these incredible results. So you've got less data, smaller models, and better performance. It's the whole package. This table just lays it all out and really drives the point home. Look at the crazy size reductions. For one language task, the student model was over 2,000 times smaller. For another one, over 700 times smaller. Even for really tricky common sense reasoning, the student was a staggering 45 times smaller than the giant model it learned from and then beat. So what does this all mean for the future of AI? I mean, this isn't just some clever trick researchers figured out. This could be a fundamental shift that changes everything about how we build and use artificial intelligence from here on out. The implications are just huge. This makes truly powerful AI accessible to way more people and companies, not just the ones with gigantic data centers. It means we could soon see incredibly smart AI running super efficiently right on our phones, in our cars, on all our everyday devices. It basically democratizes AI and could dramatically speed up the pace of innovation for everyone. And you don't have to take my word for it. As the researchers themselves put it, this method fundamentally breaks the old trade-off. You no longer need a massive model or a mountain of data to get top-tier performance. You really can have the best of both worlds. And that leaves us with one last fascinating thought to chew on. For so long, the path to more powerful AI was just to build bigger and bigger models. But if that's not true anymore, if small and smart can actually beat big and powerful, what kind of new frontiers does that open up? What incredible things are we going to build when the only real limit isn't our hardware, but our own imagination?